Hello, everybody. I guess it's Harvard. It's traditional to start 5 minutes after the hour, so maybe we should we have a tight schedule. Sorry?
You have to talk for a minute.
No. Okay, well, it's a great pleasure to welcome you all to this celebration of Bert Halperin's 75th birthday. We have a busy afternoon of talks, including a reception in the library at 3 p.m., so we do need to keep on time. So without further ado, I'll welcome our first speaker, Jim Eisenstein from Caltech.
Okay. Well, thanks very much for the invitation to do this. It's really quite an honor to come here and talk at Bert's birthday party. I've known Bert all of my scientific career, from when I was a postdoc at Bell Labs until now. And I remember learning one thing very, very early on. This is when I was doing my very first experiment at Bell Labs. Bert was visiting, and he came into the lab, and he wanted to know what I was doing. I'd never met this guy before. And I rapidly concluded that he knew more about experimental physics than I did. Now, you could say that's not such a big deal because I was very young. Unfortunately, it is still true. So that's a statement about me, I guess, more than it is about Bert. But I've always found interacting with him to be one of the most profitable things that I could do as an experimentalist. He has an unbelievable eye for experiments and asking the question that you didn't think of when you were doing your work. So I'm going to talk today. There's a title of my talk up there. This is a topic that I've just started on in the last couple of years, since I kind of actually more or less retired myself, and I'm working alone in the lab and having a really good time. And so this is a new topic for me, and I'm going to hopefully you'll find it interesting too. So spin-dependent tunneling in the quantum Hall regime. So tunneling is a very simple idea. We have these double quantum wells where we have two-dimensional electron gases in both quantum well, and we can connect wires to the individual two-dimensional electron systems and tunnel current from one to the other. And this turns out to be an interesting thing to do. It has been for a long time. Only the new thing now is that I can do it in a spin-dependent way, and that's what I'm going to tell you about. So let me give you an introduction to begin with, to help motivate why this is interesting, at least to me. So here's a picture of the tunnel spectrum, meaning the current voltage characteristic, in the lowest Landau level. So the filling factor is 1/2 in each of the two layers. It doesn't have to be precisely 1/2, but that's what this picture is. And you can see the tunnel spectrum is very broad and spread out over many millivolts in energy. And in fact, that energy is basically the Coulomb energy for particles in the lowest Landau level. It's the Coulombic, it's of order the Coulombic repulsion between the particles. So you can learn immediately when you start doing experiments like this that the tunnel spectrum is totally dominated by Coulomb interactions. Sort of single particle effects like the disorder potential have very little impact on this spectrum. One of the things that's interesting about it is that at very low, see if I can make this thing work correctly. At very low energies, you see the tunneling is very much suppressed. And this is something which, again, is a correlation effect. It's an interaction effect. It's not a gap that's real in the sense it's not a thermodynamic gap. There's no fractional quantum Hall effect at half filling. But this gap is in fact, a many-body effect as well. And this pseudo gap that exists at low energies was studied by a number of theorists back after we discovered it in the early 90s, including Bert and Phil Plassman and a young theorist at Bell Lab named Song He. And they made a theory of what this causes this strong suppression of the tunneling. And the basic answer is that at really low energies, if you tunnel an electron in really rapidly, the electron gas is so strongly correlated, even though it's not in an incompressible quantum Hall state, so strongly correlated the electrons can't get out of the way very quickly, not nearly quickly enough to accommodate this incoming electron. So the tunneling current, as a result, is strongly suppressed in a way that depends on the conductivity of the electron gas. So this was very interesting, and it's not what I'm going to talk about today, but that sets the stage, I think, for what I am going to talk about. So the next thing I want to tell you is something that I think even Bert doesn't know the answer to yet. He will know, because I haven't told it to him yet, so he'll know by the end of the talk, I suppose. Is if you do this experiment again, but now you do it at filling factor 3/2, and for those of you that aren't quantum Hall people, let me just tell you that these should be the same, these two graphs, the red curve and the blue curve. These two experiments were done at the same magnetic field. So I took a sample and I adjusted the electron densities in the layers so that they came out to both be at the same magnetic field of 4 Tesla, and the tunnel spectrum just doesn't look the same. And if you believe in particle-hole symmetry, they should be the same, and they're clearly not. The 3/2 tunnel spectrum, which is the red one, which I've sort of done these band diagrams or these lambda level cartoons on the side, has half filling of the upper spin branch, whereas the other one has half filling of the lower spin branch. These things are symmetric situations, and if there's no lambda level mixing, they really ought to be the same, and they're just not. And I've known this for many, many years, actually, since our very first experiments. And I want to know what's going on with this, and I've not yet figured it out. So that's one of the big motivations for these round of experiments. So there's some big breakdown of particle-hole symmetry. I was having a nice lunch today. We were talking about particle-hole symmetry, and I commented that I've actually never seen it in any experiment that I've ever done, that it really works. It doesn't seem to ever happen. So this is a gross example of it not happening. So lambda level mixing is one thing you can think of for breaking particle-hole symmetry. Maybe that's what's going on. Presumably it has to be at some level. Maybe the spin of the electron is doing something non-trivial that you don't understand. We don't know. I had my bets are on spin, and I'm going to show you what we've learned about that. But to start this story, what I'm going to do is I'm going to back up and tell you that I want to do experiments where I understand what the spin state of the electrodes really is. So in the 1/2 state and the 3/2 state, maybe I don't know, but maybe I can come up with some circumstances where I do know so that I can use those later on to build up a knowledge for what's going on in this 3/2 situation. So let's look at a different case. A case where I've made the two layers have different densities. Filling factor 5/2, so that's filling up more lambda levels, and filling factor 7/2. Well, 5/2 and 7/2 are both in the first excited lambda level, but in the simplest picture, they would have opposite spin states. One would be spin up at the Fermi level, one would be spin down at the Fermi level. So and if in fact it's simple like that, so you could make this device and you could ask, what does the tunneling look like in this circumstance? Well, it's easy to think of what it ought to be. This is at zero bias, no voltage between the layers, so the Fermi levels are equal. If I make the Fermi levels separated, and I do it in what I call forward bias, moving the orange electrons up higher in energy, well, they're going to tunnel. There's plenty of empty states of both spin populations for the electrons to go into. You don't have to break spin conservation for this current to flow. There should be a lot of current. On the other hand, if you go into negative bias, there shouldn't be any current at all. Because now, unless there's something in the tunnel barrier or some other process that you don't have in mind to flip the spin of the electron, or this diagram is just completely wrong, there shouldn't be any tunnel currents at all. So this thing should make a diode. And if I find that this is in fact what really happens when you make this experiment, then I've got a device whose spin structure I basically understand, and I can use it to look at other circumstances. So that was the motivation. Now, again, I have to back up a little bit and tell you that we looked at this situation carefully. I shouldn't say we, it was me. Looked at this situation carefully at both the balanced situation, 5/2 and 5/2, and 7/2 and 7/2, to make sure that nothing funny was, no surprises were there that we hadn't already, should have known of in advance. So here are the tunnel spectrums for filling factor 5/2, and you notice there's no double peak. It's a little bit like the 1/2 case. It's just a big broad peak, and again, it's comparable to the Coulomb energy. There's a pseudo gap forming at low energies. You can see it there, but it's very weak. But this data is taken at 0.8 Tesla. Don't ask why, it just was. And so it's very, very weak. So this looks okay, no big surprises. Now you do the same experiment at 7/2 by adjusting both densities so that we want to compare apples to apples, so I keep the magnetic field fixed. And we say 7/2 looks the same, okay? This all looks fine. No big surprises here. No repeat of the 1/2, 3/2 mystery. This doesn't happen in the second lambda level, okay? Well, that's 2 sanity checks that we just did, and let's do some more. As I told you, lambda level mixing could be one of the reasons that we have broken particle hole symmetry, so we can check into that a little bit, again by doing tunneling. We do the tunneling in the following way. So these are cartoons of the wave functions in the Landau gauge of electrons in the first excited Landau level. They look like harmonic oscillator wave functions, but it's the first excited state, so there's a node in the wave function at the origin. And the red ones are in one layer, and the blue ones are in another layer, and I'm going to tunnel. And I have no disorder, or very, very little, so I have to conserve momentum. Momentum in this case means that I'm going to jump from one layer to the other at the same physical location. Okay? On the other hand, if I were to apply a tilted magnetic field, keeping the perpendicular component the same. Then there's another change in the momentum coming from the Lorentz force due to the parallel magnetic field that gives me an additional momentum and changes how you have to tunnel in order to conserve canonical momentum. You have to tunnel to a state that's on an angle, the same angle that the magnetic field makes with respect to the perpendicular. Okay? So you can see what's going to happen, right? One thing, if the parallel field gets too big, these wave functions aren't going to overlap at all. And there's going to be no tunnel current, or very, very little. If you work out the arithmetic of this, you find out for the first excited Landau level, there's a form factor that comes from the shape of these wave functions, which is very easy to write down. You can just work it out. Here's the part I just mentioned, the thing that will cause everything to fall away at very large parallel fields. This Q is proportional to parallel field. But there's also this polynomial factor in front. And that comes from the shape of the wave function, the fact that it actually has a node in it. So you can ask, well, this is a nice cartoon. Does it really work? And you bet it does. It's amazing. You do this and you measure the tunneling current as a function of this parallel magnetic field, which I parameterize with this variable Q. The dotted curve is just that formula. And there are no adjustable parameters at all in this. And you can see that the tunnel current vanishes at about √2, which is QL equal to √2, which is exactly where it's supposed to vanish. So what do you learn from this? Well, you learn that kindergarten quantum mechanics works really well. It's remarkable how well it works. Momentum is apparently conserved in this experiment to a pretty good degree, at least momenta at this scale of momentum transfer. And that Landau level mixing maybe isn't too terribly important. Because if it were, if the electrons in one of the layer were 30% in the wrong Landau level because of some Coulombic mixing, it'd be kind of hard to imagine that it would work this well. But it does. That's the fact of it. Okay, so that's very pretty and nice. All right, now let's go back to the original motivation, original idea that I had for you with making this diode. So we can do this by, again, adjusting the densities in the two layers, making them come out to be 5-halves in one layer and 7-halves in the other layer, and sure shooting, it's a diode. There's a lot of tunnel current in positive bias, big peak, and very little current in negative bias. Now there's stuff going on off the edges of the graph that I'm not showing you, so maybe someday I'll show you that, but not today. Those are at higher energies and the other things that can happen, and I'm not going to go into that. So this just works really, really well. And what it means is that to the extent that that's almost a perfect diode, your assignment of what the spin configuration is from the cartoons is apparently right. This is by no means obvious that it should have come out this way. At half filling and 3-halves filling, we know that the spin states are all mixed up. But at 5-halves and 7-halves in the next, just in one more Landau level up, they're apparently doing the simplest thing they could do. They line up according to sort of Hund's rule. Okay, so this is nice. This worked out pretty well. There's the same spectrum at 5-halves. I just wanted to show you that again for comparison. All that current that you saw in negative bias for the 5-halves case is basically gone. There's something else you can see in this picture, and that is that the peak at positive bias got much bigger, and it also moved off higher in energy. Well, that's easy to understand if you think about these pictures, the cartoons that are here. When you slide this guy upward, that's positive bias, you get tunneling from both the half-filled state here and the fully filled state here in the 7-halves layer into these empty states in the other layer. And furthermore, you have to push it up farther in energy. Why? Because there's an additional splitting, the Zeeman split, not the Zeeman splitting, but the spin splitting between the energy levels, which you measure directly from this experiment. That shift in the peak is nothing but, we call it the exchange-enhanced Zeeman energy, or whatever you want to call it. It's the energy required to flip a spin, and it comes out to be about 3 Kelvin, which is a reasonable number. It's not something I can compare to a theory, but it's a reasonable number. All right. Now, 3 Kelvin is a big temperature. The energy scale is large. So if I do things at small temperatures, I wouldn't expect much to happen. But in fact, a lot happened, as you can see from these two graphs. The blue graph was the one I showed you before at 50 millikelvin, and the red graph is at 200 millikelvin. Both of those numbers are small compared to 3,000 millikelvin. And yet a lot of tunnel current now starts to appear at negative bias. What this is telling you is that the electron gap, this picture, is breaking down rapidly as you increase the temperature. The spins are getting reversed at a temperature scale which is not apparently governed by the exchange-enhanced Zeeman energy. The peak position didn't move, as you can see, but more current appeared in the negative bias. And I can tell you already that Bert had some interesting suggestions for me about why this might be when I saw him last in Santa Barbara. What I think is going on, and this is some more data showing the same thing, the growth of that negative bias peak as you increase the temperature. If you look at that on an Arrhenius plot and kind of say, what's the energy scale for this? Well, it comes out to be the bare Zeeman energy. Not this exchange-enhanced Zeeman energy, but just the energy required to flip a spin. It's the one that you would have calculated from, again, sort of simple-minded arguments. So it seems as though it's the bare Zeeman energy that's governing the temperature dependence, and I think that makes sense because of a calculation that Kathy Cowan and Bert Halpern did a long time ago. So this is a calculation of the spin wave spectrum. This is for nu equal 1. It's not for nu equal 5/2 or these other situations, but you know, I can see Kathy's not too mad that I'm using it here. There's the spectrum for spin wave excitations, and at long wavelength, of course, you know, by Larmore's theorem, they're going to go down to the bare Zeeman energy. So you're thermally populating these states, and they are causing the polarization to get reduced. At least that's what I think is going on. This is provisional until Bert explains to me why it's not true. Okay, so we're back to this puzzle. And I can see that I didn't give nearly long enough talk, but that's probably a good thing. We're back to this puzzle. What's going on here with this? So 3/2, again, I draw the picture. It's similar to what we were talking about before. So now that I've created this system where I understand the spin structure of the 5/2 and 7/2 state, why not use those to tunnel into 3/2 and see if you can figure out what's going on? Okay, so that's the plan. By the way, I have to tell you, the answer is I don't know, but I'll show you a few more steps why I don't know. So here's the 3/2 data again, but now I'm putting on the parallel field like I told you before, only now I'm in the ground lambda level, so that little polynomial factor that was there is not there anymore. It's just the Gaussian. And there's no node, so this is the shape of the wave function in the lowest lambda level, it's just a Gaussian. And again, it agrees essentially perfectly with what you would have calculated naively. So either lambda level mixing isn't very strong, or somehow it doesn't show up in this experiment for some reason that I haven't figured out yet. I don't understand why that's happening. Okay, there was something else I was going to say about that.
This is the maximum.
Yeah, I should be careful about this. So what have I actually plotted? I've plotted, well, you see different symbols here. I took each of the critical points, like that peak, that peak, that peak, and that peak, and plotted them all. Normalized by what their heights were at 0 parallel field. That's the natural thing to do. Okay? And they all lie on the same curve. And if you do the same experiment again, Bert's shaking his head. This is bad.
I'm shaking it in amazement.
Okay, good. If you do the same experiment at filling factor 1/2, I didn't show that today, but you get exactly the same curve. You get the Gaussian, which you should. It's in the lowest lambda level. So it's all kind of okay, but a little mysterious, because it's lambda level mixing that has to somehow be at the heart of what this problem is. Okay, so here we go again. Now I want to do the tunneling from 3/2 to from 3/2 and 5/2. Well, you run into another problem immediately. They're not in the same lambda level, right? So even if even if everything else works out well, there's going to be orthogonality of these states. You're not going to get any tunnel current, right? So you have to find a way around that, but that's easy. The parallel field rescues you again. They're only orthogonal if the magnetic field is perpendicular to the plane. So let's see if that works. So there's the tunnel spectrum for 3/2 into 5/2. Looks kind of similar to the one I showed you before, but you look in detail, it's not the same. There's a gigantic peak out at positive bias, which is occurring right around the cyclotron energy, not the spin flip energy, but that's what you would expect, right? Because if you make enough bias between these two things, you get the n equal 1 lambda level to dump charge into that completely empty n equal 1 level in the other layer, and the 3/2 filled guys in the ground lambda level tunnel into some empty states in the ground. Everybody's happy. It works fine, okay? And in reverse bias, well, there's something going on, but it's not huge. But there's something going on. In fact, it even smells like two peaks over here. And then again, something at vicinity of the cyclotron energy. So let's now put on the parallel field and see if we can turn on the interlambda. This is all, that peak is intralambda. I always get those two words mixed up. It's intralambda level. Let's now turn on the interlambda level by turning on parallel field, see what happens. Boom, not yet, there, it happened. And you see two things. One is the intra-lambda level peak got smaller. Well, it's supposed to. Remember the Gaussians that I showed you, that you're rolling off on that because it's both in the first excited lambda level or in the ground lambda level. And in fact, if you just assume that those two currents, one from n equal 1, one from n equals 0 lambda level, are completely incoherent, and just take the sum of the two terms, you're going to get basically exactly that amount of suppression. Works beautifully. And where these things work so well, it's actually frightening. That's something that we're really not understanding why it's working so well. On the other hand, in reverse bias, where you really are tunneling from the n equal 1 lambda level into the n equals 0 lambda level, well, it got much bigger now, which was good. So it did what we hoped it would do. It turned on. It was apparently already there. Maybe the magnetic field wasn't exactly perpendicular. It was pretty close. We work hard on that. But maybe something else is going on that breaks the orthogonality argument that I was trying to give you. I don't know. But at any rate, we certainly got a big amplification of this. OK, one more thing that you see is this little guy. Okay, this little guy is not at the interlambda level transition, excuse me, the intralambda level transition. It's at much lower energy. And in fact, it's tunneling between 5-halves and 3-halves. And it's telling you that there must be empty upspin states in the 3-halves layer. So the 3-halves layer, again, the way I've defined up and down is, in the cartoon picture, 3-halves is a fully filled lambda level upspins and a half-filled lambda level of downspins. And if that's the case, then when I go into positive bias, which, again, you don't know this, but if I move the oranges up relative to the greens, there shouldn't have been any current until I hit the next lambda level, until I get to the intralambda level peak. But there is a little peak there. So that's telling you, I think, spectroscopically, that something which we probably already knew, and that is that 3-halves is, the spin diagram for 3-halves just doesn't look like this. It actually is partially spin polarized, that both spin states are occupied at the Fermi level, not occupied, that there's empty states in both spin levels at the Fermi level. Okay, so that we've learned from this experiment. Again, as I said, we probably already knew that. But then we get the nice double peak structure. It's coming out again. So what do we learn from this? Well, at this point, I don't know. That's there. One might say, and this would be false, one might say, well, if the exchange splitting in the 5-halves layer is not equal to the exchange splitting in the 3-halves layer, and when you slide the two of them past one another, you're going to get two peaks. And that's true. But remember what I told you at the very beginning of the talk, is that if it's 3-halves and 3-halves, you still see these same two peaks. So that's not the correct explanation for why we see it in this particular experiment. Something else is happening. And I have a bunch of data where I tunnel 7-halves into 3-halves, because that's the opposite spin state. And I'm not going to show you any of it yet, because I don't understand it. So maybe, Bert, maybe by 85th anniversary, 85th birthday, I can come back and tell you what happens. It's with 7-halves tunneling into 3-halves, but not today. It's just too premature. So it's still a puzzle. What do you do when you have a big puzzle like this? You go ask Bert and see what's going on. Happy birthday, Bert.
So we have some time for questions. We'd like to use the mic for the questions so that the whole session is recorded. So, any questions?
Could you go back one slide, please? So this little blue peak at positive bias,
Yeah.
does that have a temperature dependence? Can you extract an activation energy associated with it or something?
It's a good question. I don't remember, but I think I know the answer, but it's with an asterisk that I'm not very good at remembering. The answer is I don't think it has much temperature dependence at these same low temperatures like we were showing before. It is certainly true that those double peak structures, when you do the 3-halves experiment, shows very little temperature dependence until you get to much higher temperature, a temperature of order the kinds of energy scales you would guess from where these where these peaks are in voltage. So I believe the answer to your question is no, but we better leave an asterisk on it.
Okay. So I shouldn't think that little blue peak has the same Beer-Zeeman energy, activation energy.
You should not think that, right? Until I change my mind.
If you look at the tunneling current as a function of voltage and parallel field on the two-parameter plane. Can you see peaks moving or something like that? Can you see indications of modes?
So let's see. Again, I didn't bring that data. So I have a lot of data which shows 3/2 into 3/2 as a function of parallel field. And I showed you the amplitude suppression effect being the Gaussian. And if my memory serves correctly, and I'm pretty darn sure I'm right about this, they do very little moving as a function of parallel field. What does happen, as you can guess, is that another peak, an interlambda level peak, develops, which grows very rapidly with in plane field. But the peak positions do not change very much. No, they do not. I should also add, just as although I focused on these half-filling states, we're doing that because they're convenient states to work at, not for various technical reasons. It's not because the physics is specific to these filling factors. So you go away from 3/2, to 1.6 or something like that. The splitting is still there. There's kind of a dance that goes on in the relative amplitude of the peaks, but the splitting is still there. And it's never there in the 1/2 case.
So you show that tunneling is suppressed when you have opposite spins. And I wonder if there's anything that you can do to turn on tunneling between opposite spin states, like apply microwaves or put some impurities or things like that.
Well, I think the answer is yes, but I haven't done any of them. One thing I didn't say when I showed that temperature dependence, maybe I put it back up there if I can get it to it quickly. Yeah, this one. That at low temperatures, both of these two data sets, incidentally, were just at different magnetic fields, so there's not any important difference between them. They both saturate. Now, one possibility is that saturation is really uninteresting because I don't have the electron temperature under control. I don't think that's right, but it's always a possibility. Another possibility is that the system at 7/2 and 5/2 is in fact not maximally polarized, but there's a little bit of the other guy at the Fermi level. And the third possibility is something, well, maybe not the third, but another possibility is that there are some spin flips going on, coming from other things, disorder of some type in the barrier that we don't control. Spin orbit effects, which I've not said a word about, could all be responsible for that. So you could probably have fun actually putting known things inside the tunnel barrier, or maybe with the microwaves, I haven't thought about that, but it'd be interesting. I have not done it though, not intentionally anyway.
Any more questions? Okay, well, thank you very much, Jeff.
Sure. That's fun.